Chapter 25. Up to this point, we've been looking at electrodynamics, and we've been looking at things to kind of correlate it where we were in Physics 1, that being kinematics and forces and dynamics like that. And so we made those correlations to try to make the understanding of these fields that you can't see a little bit easier if you can correlate it with things you can see, like mechanical motion and that sort of thing. We've gotten to the point, though, where we should consider an energy approach to electrodynamics. We saw that in Physics 1, that we could look at these complicated force problems with vectors and free body diagrams, and we could actually solve a lot of those difficult problems much more easily if we consider energy and the one equation to rule them all. We want to do the same thing with electric fields, and that's the approach in this chapter. Consider this. Let's say you did some work on a charge by applying a force due to an electric field, and the infinitesimal amount of work you would do would be equal to that force dotted with its displacement. So it would be QE dotted with ds, being the infinitesimal displacement. Now, that work has to come from somewhere, and in the absence of having a special force elsewhere, if it's from the electric field, then the work is going to come from the electric field. The electric field will lose some potential energy by doing that. So the change in potential energy of the electric field will be equal to the negative work done on the charge, which will be equal to negative Q times the summation of all these infinitesimal amount of works done on the charge as it moves a displacement, which is going to be equal to the integral from A to B of the field dotted with the displacement. This is going to be a conservative field, so that's why we're going to just treat the work done as being a potential energy, and that way we don't have to worry about this aspect of work done. It's all going to be a potential energy function. We're going to define the change in potential as being equal to this negative integral from A to B of the E field dotted with displacement. If we make this definition for what we call change in potential, designated by V, this becomes a simple mathematical relationship. The change in potential energy is equal to the charge times the change in potential. Very simple relationship, making this mathematics real easy to do. Consider, for energy, the one equation to rule them all that we talked about in Physics 1. Basically, it looks like this. If we had 2 points, A and B, the kinetic energy at A plus the potential energy at A plus any work done along the way should equal the kinetic energy at B plus the potential energy at B. In this case, we're only going to have work done by the conservative field, so there will be no work done by any other external forces. So we can assume that that's going to be 0. And we'll only deal with the work done by the field in terms of this idea of potential energy. So, rearranging, we have that the kinetic energy at B minus the kinetic energy at A plus the potential energy at B minus the potential energy at A is equal to 0, or we can write this as our change in kinetic energy plus our change in potential energy equals 0. This statement, a very simple statement, is really a statement of our one equation to rule them all that we want to use in an electrodynamic sense. A very simple equation, but very, very useful. And in fact, if we go one step further, we can write this as saying that the change in kinetic energy will equal the negative change in potential energy. If we use the opposite statements on this screen, the top statement being the change in potential energy equals charge times change in potential, and the bottom statement saying that change in kinetic energy is a negative change in potential energy, these two very simple statements will take us a long ways through handling problems in this chapter. Let's try it out. Here's problem number 3 on your problem set. A particle charged 2 millicoulombs, moving in a region where only electric forces act on it, has a kinetic energy of 5 joules at point A. The particle subsequently passes through point B, which has an electric potential of 1.5 kilovolts relative to point A. Determine the kinetic energy of the particle at point B. Alright, so we know our change in potential energy will equal our charge times what we call the change in potential. Our charge is 2 millicoulombs, 2 times 10 to the minus 3 coulombs. Our change in potential, we went higher, 1.5 kilovolts higher at point B relative to point A. So our change in potential is 1,500 volts. 10 to the minus 3, 10 to the 3 cancel out. And our change in potential energy is 3 joules. Since our change in kinetic energy plus our change in potential energy is 0, we have that our change in kinetic energy is a negative change in potential energy, which would be a negative 3 joules. Our change in kinetic energy is our final kinetic energy minus our initial kinetic energy. In this case, our kinetic energy at B minus our kinetic energy at A. So our kinetic energy at B will be equal to a negative 3 plus our kinetic energy at A. But we're told that the kinetic energy at A was 5 joules. So we have a negative 3 plus 5 is 2 joules. So our final kinetic energy, the kinetic energy at point B, is indeed 2 joules. That's our answer. Very simple mathematics, but we have to be able to understand the problem in order to utilize these simple equations. Consider this change in potential, this delta V that we've been talking about. In a uniform electric field, uniform being a constant field, we could possibly get that if we had 2 parallel large charged plates. And between those plates would be a constant electric field. And if we had a constant electric field and we had a displacement of a charge along that field, like a ds, then they both would be in the same direction. So the E field is constant and parallel to our displacement ds. If that's true, then E dot ds would be equal to E ds cosine 0. And the E field will be constant, so we can take it out of the integral. So now we have our change in potential, delta V, is equal to a negative E, displacement ds from A to B, and that's simply going to be the distance from A to B. So that's going to be equal to negative E times D, where D is the distance that we traveled. That's a very unique case. It's only for a uniform electric field case, but this comes up quite often. So this could be a very useful equation to use. The change in V is equal to negative E times D. Here's how it might look. We have 2 charged plates. We have a uniform E field between them. If we had a positive charge starting at an initial position where this V sub I is, it's going to fall to a new potential, V final. In other words, in a dynamic sense, it's going to be repulsed by its positive plate and attracted to the negative plate. So it's going to move towards the negative plate. But in essence, it's going to fall from a higher potential to a lower potential. And its change in potential will be a negative E times that distance D. Likewise, I could have a negative charge, which in a dynamic sense would be repulsed by the negative plate and attracted to the positive plate. It will fall in that direction, which will be in the opposite direction of the E field. So its change in potential again would be a negative E times D, but the displacement or the dot product between the E and D will be a negative value. So it will rise to a higher potential as it goes from this position to the final position. With this definition, for a constant E field case, the change in potential energy will be equal to the charge times the change in potential, which would be a negative QED. And again, we can think of this just like we have in mechanics of a changing potential energy. Changing potential energy falling in an electric field means our final potential energy would be less than our initial potential energy. Hence, we'd have a negative QED. Just like a mass falling in a gravitational field, where our final potential energy, mgh, would be less than our initial potential energy of mg higher h. And so we'll have a change in potential energy in that case of a negative mg d or h, whatever the distance was between those two positions. So we can think of it in a similar way in terms of fields. Let's kind of summarize this mechanical analogy. If I had a gravitational field, I'm going to deal with a mass. And the force on that mass is going to be mg, the mass, the object mass, times the field, g. The energy associated with its position in that field is mgh. Let's make our analogy. For electrodynamics, we have an object, which is a charge. Its force is the charge, the object, times the field, E in this case, and its position within a constant field is associated with QED. How about that? The System International Unit for potential is called the volt. The volt is a joule per coulomb. This volt is the same volts that we're going to talk about when we get into circuits, dealing with potential in circuits. So it eventually will be our segue into circuits, which is coming up. Not today, but coming up in future chapters. With this definition of the volt, there are now two possible units for the electric field. We did have newtons per coulomb in the SI system, but now we could just as equivalently have volts per meter. They are exactly the same unit in the System International or metric system. A newton per coulomb is exactly the same as a volt per meter. So you might see some problems where they give you the electric field in terms of volts per meter as far as your units. Also, we may have what is called an electron volt, which is a unit of energy that an electron or proton will gain or lose by moving through a potential difference of 1 volt. In other words, electron volt would be equal to the charge times the change in potential. 1.6 times 10 minus 19 coulombs times 1 volt will give us 1.6 times 10 minus 19 joules. So 1 electron volt is 1.6 times 10 minus 19 joules. We're not going to deal a lot with this electron volts in this particular course, but if you were dealing with subatomic particles and dealing with changes in potential a lot on that level, then you would deal a lot with electron volts. And in some branches of physics, that would be very important, especially possibly in physics 3 or in chemistry. Let's try out this idea of potential difference in an electric field. A proton in an electric field of 8 times 10 to the 4 volts per meter travels a distance of 0.5 meters. Find the drop in potential. So we have a constant field, so our change in potential is going to be equal to negative E times D. Negative 8 times 10 to the 4 times 0.5 meters is a negative 4 times 10 to the 4 volts, or a negative 40,000 volts. In other words, a proton being a positive charge fell in this field by 40,000 volts. The change in potential energy is the charge times the change in potential. That's going to be 1.6 times 10 minus 19 for the proton. Negative 40,000 volts will be a change in potential energy of a negative 6.4 times 10 minus 15 joules, which means that the field lost its potential energy as the proton was gaining kinetic energy. Let's find the speed of the proton after it's moved 0.5 meters. Well, we know the change in kinetic energy plus the change in potential energy should equal 0. So the change in kinetic energy is equal to the negative change in potential energy, which would be a positive 6.4 times 10 to the minus 15 joules. Since our change in kinetic energy is our final kinetic energy minus our initial kinetic energy, and we start from rest, so our change in kinetic energy is simply our final kinetic energy, 1/2 mv squared. We can rearrange this to find our final speed. Multiply both sides by 2, divide by the mass, take the square root, and our final speed is 2 times the change in kinetic energy divided by the mass. 2 times 6.4 times 10 minus 15 joules over the mass of a proton, 1.67 times 10 to the minus 27 kilograms, square root, will give us a speed of 2.77 times 10 to the 6 meters per second. You may recall that the speed of light is 3 times 10 to the 8 meters per second. So this is roughly about 1/100th the speed of light. So we're not quite relativistic yet, but if we went much faster than this, we'd have to worry about relativity, which says that there's a speed limit to the universe. So we can still use 1/2 mv squared for kinetic energy if we're at these kind of speeds. But if we went much faster than this, we'd have to use the theory of relativity, which we're not going to use yet in this course. So we're okay so far. Equipotential surfaces. On an equipotential surface, all points are at the same potential. No work is required to move a charge over that equipotential surface. The electric field will be perpendicular to this surface everywhere on the surface. For example, an equipotential surface can be expressed at a distance from a point charge. A point charge is an electric field producing device. It has electric field emanating away from it radially outward in all directions, and around it would be equipotential surfaces. So we're looking at it two-dimensionally in this little picture here, but you can imagine that it's a three-dimensional sphere around this charge at different radii, and each sphere is an equipotential surface. So if I brought in another charge and put it on that surface, it could move around everywhere on that sphere and never change the potential energy of that system because it would maintain the same distance away from the first charge. As long as you're on the equipotential surface, no work is required to move on that sphere. So it takes the same amount of work to move from point A to point B, where you're changing from one equipotential surface to another, as it would to go from A to C, because from B to C there is no work done. So from A to B it's the same as from A to C in this case. No work done on the equipotential surface from B to C. Dealing with these equipotential surfaces, where they all seem to be concentric, kind of brings to mind the idea of contour maps that you might associate with geography. And so I want to bring up that analogy because it's going to bring this concept of potential possibly clear in an intuitive sense. Recall a geographical contour map like this one right here. We have concentric lines. No two lines cross, so you always have these lines, but they never cross, and they're always designating the same height within the contour. So if you made a map of these different heights, you would actually be making a two-dimensional mapping of a three-dimensional contour. This map in particular represents one of these four contours that we see in the pictures to the right. Which one? Well, we know it's not Mount Rushmore, because if we were looking at this map, we probably would see features that show the contours of the faces of Mount Rushmore, so that's out. We know it's probably not Mount Rainier because it looks like we got a flat top here, and Mount Rainier is kind of pointed at the top, so that's not going to work. So it's either the Devil's Tower or this hole on the right. I forget the name of the hole. It's one of those two. And if we actually looked at the values of the contours, we'd see that the value of the height is going up as we're going towards the center. So we imagine that the elevation is going up as we go towards the center, so the hole is out. So it's actually this Devil's Tower, which I don't recall exactly where that out west that's located. So we have this contour map associated with this Devil's Tower, which actually was the focal point of the movie Close Encounters of the Third Kind. I was supposed to have a dun 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 music here, but it's not going to play while I'm talking to you, so that would be fruitless. But imagine that we have a charge, a positive charge, and if we were to map the potential around that positive charge, it might look like this contour map associated with the tower, where we have these separate contours representing a steepness of the slope. So in other words, the potential values are kind of associated in a sense with the height within the field. If I were to associate with a contour map of geographical proportions, it is the height within the field that the potential represents. This negative charge, conversely, could be the hole. So where we have a lot of these lines of potential, we can imagine that things are pretty steep there as we go from a higher potential to a lower potential, and where the density of these circles are greatest, we have our greatest amount of slope, and hence we have our greatest value of electric field. In other words, the electric field is the slope of this mapping of the potential. Where the potential becomes less dense as we go further away, the electric field, which is always perpendicular, is always the slope, will be less of a value out in that vicinity. Well, an electric field producing device is indeed a charge, and so is the mapping of a potential. The potential due to a point charge is equal to K times the value of that charge over your distance from that charge. And it's a scalar value. So if it were a positive charge, it would be a positive number. And if it were a negative charge, it would be a negative number. So the energy of a two-charge system, if I brought a second charge into that point, it would be equal to the value of that second charge times the potential at that point, which is the value of that second charge times the potential due to the first charge, KQ1 over R, or KQ1, Q2 over R, R being the distance between those two charges. If we had many charges, we could plot the potential at any particular point by the superposition of this KQ over R for every charge that we had. So we would add positive or negative due to what the values of the charges were, and add them together at any particular point, connect equal points to get our equal potential lines, and then we're mapping the field like a contour map. So our potential would be K, QI over RI for all of our charges, either positive or negative, add them together like scalars, map them together, connect the dots. Our potential energy would be K, QI, QJ over the distance between every pair of charges. And we could add this for all the pairs that we'd have and get our potential energy for the system. We're not going to use this too much in our course right now, but it's something that could be useful later on. So for a constant field, we have the change in potential is negative E times D. For a point charge, it's not constant. It's KQ over R, and so it varies as your distance, it goes down as your distance from the point charge. Much more intense as you get close, and then drops off as your distance. But it's a scalar value. If we had a system of charges, we just add up all these scalar values at any particular point, and that gives us the potential at that point. Let's try this out. Point charges Q and big Q are positioned as shown. If little q is 2 nanocoulombs, big Q is minus 2 nanocoulombs, A is 3 meters, B is 4 meters, what is the electric potential difference, VA minus VB? Well, we just want to find the potential at point A, find the potential at point B, and subtract the two. At point A, we have KQ over R1 plus K big Q over R2, our scalar potential due to these two charges. Note that big Q is 5 meters away because A is 3 and B is 4, and we have a 3, 4, 5 triangle. So the distance from big Q will be 5 meters. We have K 9 times 10 to the 9. Little q is 2 nanocoulombs. It is 3 meters away from point A. Big Q is minus 2 nanocoulombs. It is 5 meters away from point A. And it's going to be negative. If we add these together, 10 to the 9 and 10 to the minus 9s cancel out. So we have 9 times 2/3 plus a negative 2/5, which gives us 2.4 volts. That's the potential at A. What's the potential at B? Do the same thing. KQ over R1 plus K big Q over R2. Now at point B, it's little q that is actually 5 meters away because A is 3 meters, B is 4 meters, and we have ourselves a 3, 4, 5 triangle there. So little q is 5 meters away, big Q is only 3 meters away. So we have 9 times 10 to the 9, 2 nanocoulombs, 2 times 10 to the minus 9 over 5 meters. And then big Q is a negative 2 times 10 to the minus 9 coulombs, 3 meters away. The 10 to the 9 and the 10 to the minus 9s cancel out. And we have 9 times 2/5 minus 2/3, which will give us a negative 2.4 volts. So the difference in potential between A and B, VA minus VB, will be the potential at A minus the potential at B. That's going to be 2.4 minus a negative 2.4, which would be 2.4 plus 2.4, or a potential difference of 4.8 volts. So that's the potential difference, VA minus VB. It's strictly scalars. It's not as complicated as vectors. It's strictly scalars in this sense, where we just map the potential and take the difference of the two. And it's a much more easier problem in that sense. This idea of contour maps is something we're well familiar with, especially when we talk about weather. If we made a contour map of pressures over a site of weather like the United States, we would be able to distinguish a lot of factors about the weather with this contour map. Here we have a pressure map, and we can see we can connect lines of equal pressure, and that would be our isobars, and that kind of corresponds to our lines of equal potential or our lines of equal height in electric fields or geographical fields, respectively. So we make these isobar lines, and then we can isolate points of high pressure. Now, high pressure means that the air is moving downward, creating high pressure at that point, hence dissipating clouds, and you have fair weather. So at high pressure, you have fair weather over here, fair weather out west here. At low pressure, that's when clouds are, when air is rising, forming clouds, and hence forming rain clouds and possibly storms. So up here in Canada at this point, we'd have a low pressure, maybe some storms down there, and then over here where the pressure goes down, here in the southeastern United States, we might have a low pressure there. So we can expect stormy weather in those locations on this particular day. But we can see that the contour map tells us a lot about the weather in terms of isobars. We know that where the pressure changes from high to low, there will be a slope there, and that's associated with the wind direction and the value of the wind, where if that slope is pretty dramatic, we'll have very high winds at that location. So the slope of this contour map is the wind direction and the wind value, just like electric field is a slope of a contour map in electrodynamics. So we can see how simplified the contour maps can make this for us in the energy perspective. And we can also understand the weather. That's our weather forecast for today. Weekend forecast yet to come. So we can start with the scalar potential, and we can get a vector electric field from that potential by taking the derivative of our components of the electric field for I, J, and K. We can construct a vector electric field from a scalar potential. How great is that? Because scalar potential is easy to set up. We just add up all the values, connect the dots, make our scalar potential, and then if we take the derivative as a function of x, y, and z, we can construct the electric field from that scalar potential. This is often represented as the electric field is equal to negative del times V. This upside down triangle is called the Dell Notation, and it's associated with trying to come up with vector results from scalar options, or sometimes vector options. So its action on a scalar potential gives us what is called the gradient operator. Gradient operator is ijk multiplied by the partial derivative x, y, and z of the scalar potential. So the Dell notation, sometimes called nabla, which was the object of the harp in the old days, so it kind of looks like a big harp. The Dell notation associated with the gradient operator on the scalar potential. If the charge distribution only depends on one spatial coordinate, and we only look at that coordinate, negative derivative of the potential with respect to, say, x, or if it only depends on a radial direction, we only look at the radial direction. So the E field in the radial direction would be a negative derivative of the potential with respect to the radial direction. Let's try this out. The electric potential in a certain region is V equal to 4xz minus 5y plus 3z squared volts. Find the magnitude of the electric field at x equal 2, y equal negative 1, z equal 3, where all the distances are in meters. Well, we're going to take the negative gradient of the potential, which would be a negative ijk partial derivative xyz of this scalar potential that we have, 4xz minus 5y plus 3z squared. Now if I do this, partial derivative of x of this function, that's something pretty simple that you know. It's always easier to take derivatives than it is to integrate. If I take the derivative, the partial derivatives are even better because you treat everything else as being constant. So we treat the 5y as being constant and the 3z squared as being constant. So the derivative of those will be 0. And then the derivative of the 4xz will just leave me with the 4z. Do the same thing, partial derivative with respect to y. Again, everything that isn't y is treated like a constant in the partial derivative. So the 4xz will be 0, and the 3z squared will be 0. And if I take the derivative of the negative 5y, I'll just be left with a negative 5. Partial derivative with respect to z, same idea. Anything that doesn't have a z, treat it like a constant for the partial derivative. So negative 5y will be 0, 3z squared will be 0, 3z squared will be 6z. So we end up with this, negative 4zi minus 5j plus 4x plus 6zk. That's my E field for all x, y, and z with this potential. Nice. At the particular point where x is 2, y is negative 1, and z is 3, we can plug those in to our E field, and we get -4 times Z was 3. Can't do anything here with the J, but X was 2 and Z was 3. So our E field at that point is a -12I plus 5J minus 26K volts per meter. If we want the magnitude of this field, we need to square all the components, even 3 dimensions, use the Pythagorean theorem in 3 dimensions. Square all the components, add them together, take the square root. So that's what we'll do. The magnitude of this field would be -12 squared plus 5 squared plus -26 squared. All that square root gives me 29.1 volts per meter. That is the magnitude of the field at this particular point of x equal 2, y equal -1, and z equal to 3. That concludes the first lecture dealing with energy and potential in chapter